Hello, I'm John Hennessy. It's my pleasure to participate in the 2021 T-Edge conference. Today, I'm going to talk to you about the trends and challenges in deep learning and semiconductor technologies, and how these two technologies, one a critical building block for computing, and the other an incredible new breakthrough in how we use computers, are interacting, conflicting, and how they might go forward. AI has been around for roughly 60 years, and for many years it continued to make progress, but at a slow rate, much slower than many of the early prophets of AI had predicted. And then there was a dramatic breakthrough around deep learning. First, several small examples, but certainly AlphaGo defeating the world's Go champion at least 10 years before expected was a dramatic breakthrough. It relied on deep learning technologies, and it exhibited what even professional Go players would say was creative play. That was the beginning of a world change. Today, we've seen many other deep learning breakthroughs where deep learning is being used for complex problems. Obviously crucial for image recognition, which enables self-driving cars, critical, becoming more and more useful in medical diagnosis. For example, looking at images of skin to tell whether or not a lesion is cancerous or not. And applications in natural language, particularly around machine translation. Now for Latin-based languages, basically being as good as professional translators, and improving constantly for Chinese to English, a much more challenging translation problem, but where we see even a significant progress. Most recently, we've seen AlphaFold 2, DeepMind's approach to using deep learning for protein folding, which advanced the field by at least a decade in terms of what was doable, a real breakthrough in applying this technology to biology, and going to dramatically change the way we might do drug discovery in the future. What drove this incredible breakthrough in deep learning? Clearly, the technology, the deep learning concepts had been around for a while, and in fact, in many cases have been discarded earlier. So why was it able to make this breakthrough now? First of all, we had massive amounts of data for training. The internet is a treasure trove of data that can be used for training. ImageNet was a critical tool for training image recognition. Today, close to 100,000 objects are in ImageNet and more than 1,000 images per object, but initially enough to train image recognition systems really well. So that was the key. Obviously, we have lots of other data we're using here for whether it's protein folding or medical diagnosis or natural language. We're relying on the data that's available on the internet that's been accurately labeled, of course, to be used for training. Second, we were able to marshal massive computational resources, primarily through large data centers and cloud-based computing. Training takes hours and hours using thousands of specialized processors. We simply didn't have this capability earlier. So that was crucial to solving the training problem. And I want to emphasize that training is the computationally intensive problem here. Inference is much simpler by comparison. And here you see the rate of growth of performance demand in petaflop days needed to train serious models here. If you look at training AlphaZero, for example, it requires 1,000 petaflop days, roughly a week on the largest computers available in the world. And this speed has been growing actually faster than Moore's law. So the demand is going up faster than what semiconductors ever produced, even in their very best era. We've seen a 300,000 times increase in compute from training simple models like AlexNet up to AlphaGo 0. And new models like GPT-3 and BERT have billions of parameters that need to be set. So the training and the amount of data they have to look at is truly massive. And that's where the real challenge comes. Moore's law, the version that Gordon Moore gave in 1975, predicted that semiconductor density would continue to grow quickly and basically double every 2 years. But we began to diverge from that really quickly diverged beginning around 2000, and that spread is growing even wider. As Gordon said in the 50th anniversary of the first prediction, no exponential is forever. Moore's law is not a theorem or something that's definitely must hold true. It's an ambition which the industry was able to focus on and keep intact. If you look at this curve, you'll notice that for roughly 50 years, we dropped to only a factor of 15 while gaining a factor of more than almost 10,000. So we largely were able to keep on this curve, but we begin diverging. And when you factor in increasing costs of new fab and new technologies, you see this curve when it's converted to price per transistor, not dropping nearly as fast as it once fell. We also have faced another problem, which is the end of so-called Dennard scaling. Dennard scaling was an observation made by Robert Dennard, the inventor of the one transistor DRAM cell that is ubiquitous in computing technology. And he observed that as dimensions shrunk, so would the voltage and other capacitance, for example, and that would result in nearly constant power per millimeter of silicon. That meant, because the amount of transistors that were in each millimeter were going up dramatically from one generation to the next, that power per computation was actually dropping quite quickly. That really came to a halt around 2007, and you see this red curve, which was going up slowly at the beginning between 2000 and 2007, really begin to take off. That meant that power was really the key issue, and figuring out how to get energy efficiency would become more and more important as these technologies went forward. The combined result of this is that we've seen a leveling off of uniprocessor performance, single core performance, after going through a rapid growth period in the early part of the industry of roughly 25% a year, and then a remarkable period with the introduction of RISC technologies, instruction level parallelism of over 50% a year, then a slower period which focused very much on multi-core and building on these technologies. And in the last few years, only less than 5% improvement in performance per year. And even if you were to look at multi-core designs with the inefficiencies that come about due to Amdahl's law and other effects, you'd see that that doesn't significantly improve things across this. And indeed, we are in the era of dark silicon, where multi-cores often slow down or shut off a core to prevent overheating. And that overheating comes from power consumption. So what are we going to do? We're in this dilemma here where we've got a new technology, deep learning, which seems able to do problems that we never thought we could do quite effectively. But it requires massive amounts of computing power to go forward. And at the same time, Moore's law and the end of Dennard scaling is creating a squeeze on the ability of the industry to do what it's relied on for many years, namely just get the next generation of semiconductor technology, everything gets faster. So we have to think about a new solution, and the new solution, there are three possible directions to go. Software-centric mechanisms, where we look at improving the efficiency of our software so it makes more efficient use of the hardware. And in particular, the move to scripting languages such as Python, for example, that are dynamically typed. They encourage reuse, they make programming very easy, but they're not terribly efficient, as we'll see in just a second. Hardware-centric approaches. Can we change the way we think about the architecture of these machines to make them much more efficient? This approach is called domain-specific architectures or domain-specific accelerators. The idea is to just do a few tasks, but to tune the hardware to do those tasks extremely well. We've already seen examples of this in graphics, for example, or a modem that's inside your cell phone. Those are special purpose architectures that use intensive computational techniques, but are not general purpose. They're not programmable for arbitrary things. They're designed to do a range of either graphics operations or the operations required by a modem. And then, of course, some combination of these. Can we come up with languages which match to these new domain-specific architectures, domain-specific languages, which improve the efficiency and let us code a range of applications very effectively. This is a fascinating slide from a paper that was done by Charles Lyserson and his colleagues at MIT and published in Science, calls There's Plenty of Room at the Top. And what they just wanted to observe is that software inefficiency and the inefficiency of matching software to hardware means that we have lots of opportunity to improve performance. They took, admittedly, a very simple program, matrix multiply, wrote it initially in Python, and ran it on an 18-core Intel processor. Simply by rewriting the code from Python to C, they got a factor of 47 in improvement. Then introducing parallel loops gave them another factor of approximately 8. Then introducing memory optimizations. If you're familiar with a large-scale matrix multiply, by doing it in blocked fashion, you can dramatically improve the ability to use the caches effectively, and thereby they got another factor of a little under 20 from that, about 15. And then finally, using the vector instructions inside the Intel processor, they were able to gain another factor of 10. Overall, this final program runs more than 62,000 times faster than the initial Python program. Now, this is not to say that you would get this for the larger scale programs or all kinds of environments, but it's an example of how much inefficiency is in, at least for one simple application. Of course, not many performance sensitive things are written in Python, but even the improvement from C to the fully parallelized version of C that uses the SIMD instructions, similar to what you would get if you used a domain-specific processor, is significant just in its own right? That's nearly a factor of 100, more than 100. It's almost 150. So there's lots of opportunity here, and that's the key point behind this slide and observation. So what are these domain-specific architectures? They're architectures that achieve higher efficiency by tailoring the architecture to the characteristics of the domain. We're not trying to do just one application, but we're trying to do a domain of applications, like deep learning, for example, like computer graphics, like virtual reality applications. So it's different from a strict ASIC that is designed to do only one function, like a modem, for example. It requires more domain-specific knowledge. So we need to have a language which conveys important properties of the application that are hard to deduce if we start with a low-level language like C. This is a product of co-design. We design the applications and the domain-specific processor together. And that's critical to get these to work together. Notice that these are not going to be things on which we run general purpose applications. It's not the intention that we take a hunk of C code. It's the intention that we take an application designed to be run on that particular DSA, and we use a domain-specific language to convey the information to the application, to the processor, that it needs to get significant performance improvements. The key goal here is to achieve higher efficiency, both in the use of power and transistors. Remember, those are our two limiters, the rate at which transistor growth is going forward and the issue of power from the lack of Dennard scaling. So we're trying to really improve the efficiency of that. Good news. The good news here is that deep learning is a broadly applicable technology. It's the new programming model of programming with data rather than writing massive amounts of highly specialized code. Use data to train the deep learning model to detect that kind of specialized circumstance in the data. And so we have good target domains here. We have applications which are really demanding of massive amounts of performance increase, for which we think there are appropriate domain-specific architectures. It's important to understand why these domain-specific architectures can win. In particular, there's no magic here. People who are familiar with the books that Dave Patterson and I co-authored together know that we believe in quantitative analysis in an engineering scientific approach to designing computers. So what makes these domain-specific architectures more efficient? First of all, they use a simpler model for parallelism that works in a specific domain. And that means they can have less control hardware. So for example, we switch from multiple instruction, multiple data models, what's in a multi-core, to a single instruction, multiple data model. That means we dramatically improve the energy associated with fetching instructions, because we only have to fetch one instruction rather than many instructions. We move to VLIW versus speculative out-of-order mechanisms. So things that rely on being able to analyze the code better, know about dependencies, and therefore be able to create and structure the parallelism at compile time rather than having to do it dynamically at runtime. Second, we make more effective use of memory bandwidth. We go to a user-controlled memory system rather than caches. Caches are great, except when you have large amounts of data that's streaming through them, they're extremely inefficient. That's not what they're meant to do. They're meant to work when the program does repetitive things, but in a somewhat unpredictable fashion. Here we have repetitive things in a very predictable fashion, but very large amounts of data. So we go to an alternative using prefetching and other techniques to move data into the memory. Once we get it into the memory within the processor, within the domain-specific processor, we can then make heavy use of that data before moving it back to the main memory. We eliminate unneeded accuracy. It turns out we need relatively much less accuracy than we do for general purpose computing here. In the case of integers, we need 8 to 16-bit integers, and in the case of floating point, we need 16 to 32-bit, not 64-bit large-scale floating point numbers. So we get efficiency there by making data items smaller and by making the arithmetic operations more efficient. The key is that the domain-specific programming model matches the application to the processor architecture. These are not general-purpose processors. You are not going to take a piece of C code, throw it on one of these processors, and be happy with the result. They're designed to match a particular class of applications, and that structure is determined by that interface in the domain-specific language and the underlying architecture. So this just shows you an example so you get an idea of how we're using silicon rather differently in these environments than we would in a traditional processor. And what I've done here is taken a first generation TPU1, the first tensor processing unit from Google, but I could take the second or third or fourth. The numbers would be very similar. And I've shown you what it looks like as a block diagram in terms of what the chip area is devoted to. It has a very large matrix multiply unit that can do a 256 by 256 by 8-bit multiplies. Later ones actually have floating point versions of that multiply in it. It has a unified buffer that's used for local activations, a memory buffer, interfaces, accumulators, a little bit of control, and interfaces to DRAM. Today, that would be high bandwidth DRAMs. Early on, it was DDR3 DRAMs. So if you look at the way in which the area is used, 44% of it is used for memory to store temporary results in weights and things being computed. Almost 40% is being used for compute, 15% for the interfaces, and 2% for control. Compare that to a single Skylake core from an Intel processor. In that case, 33% is being used for cache. So notice that we have more memory capacity in the TPU than we have on the Skylake core. And in fact, if you were to remove the tags from the cache, that number, because that's overhead, it's not real data, that number would even be larger. The amount on the Skylake core would probably drop to about 30%. So almost 50% more being used for active data. 30% of the area is used for control. That's because the Skylake core is an out-of-order dynamic schedule processor, like most modern general purpose processors, and that requires significantly more area for the control, roughly 15 times more area for control. That control is overhead, and it's energy intensive computation, unfortunately, the control unit. So it's also a big power consumer. 21% for compute. So notice that the big advantage that exists here is the compute area is roughly almost double what it is in the Skylake core. Memory management, there's memory management overhead, and finally miscellaneous overhead. So the Skylake core is using a lot more for control, a lot less for compute, and somewhat less for memory. So where does this bring us? We've come to an interesting time in the computing industry, and I just want to conclude by reflecting on this and saying something about how things are likely to go forward in the future, because I think we're at a real turning point at this point in the history of computing. From 1960, the introduction of the first real commercial computers, to 1980, we had largely vertically integrated companies. IBM, Burroughs, Honeywell, the early spinouts out of the activity at the University of Pennsylvania that built ENIAC, the first electronic computer. IBM is the perfect example of a vertically integrated company in that period. They did everything. They built their own chips. They built their own disks. In fact, the West Coast operation of IBM here in California was originally open to do disk technology. And the first Winchester disks were built on the West Coast. They built their own processors, the 360, 370 series, et cetera. After that, they built their own operating system. They built their own compilers. They even built the databases. They built the networking software. And in some cases, they even built application programs. But certainly the core of the system, from the fundamental hardware up through the databases, OS, compilers, were all built by IBM. And the driver here was technical concentration. IBM could put together the expertise across these wide set of things, assemble a world-class team, and really optimize across the stack in a way that enabled their operating system to do things such as virtual memory long before other commercial activities could do them. And then the world changed, really changed with the introduction of the personal computer and the beginning of the microprocessor takeoff. What happened then? We changed from a vertically organized industry to a horizontally organized industry. We had silicon manufacturers, Intel, for example, doing processors along with AMD, and initially several other companies, Fairchild, National, others, Motorola. We had a company like TSMC arise, a true silicon foundry making silicon for others, something that didn't exist in an earlier period, but really in the late 80s and 90s really began to take off. And that enabled other people to build chips for graphics or other functions outside the processor. But Intel didn't do everything. Intel did the processors, and Microsoft then came along and did OS and compilers on top of that. And Oracle, companies like Oracle came along and built their applications, databases, and other applications on top of that. So it became a very horizontally organized industry. The key drivers behind this, obviously, the introduction of the personal computer, the rise of shrink-wrap software, something a lot of us did not foresee coming, but really became a crucial driver, which meant that the number of architectures that you could easily support had to be kept fairly small, because the software companies that doing the shrink-wrap software did not want to have to port and verify that their software worked on lots of different architectures. And of course, the rise and the dramatic growth of the general purpose microprocessor. This is the period in which the microprocessor replaced all other technologies, including the largest supercomputers. And I think it happened much faster than we expected. By the mid-80s, the microprocessor put a serious dent in the mini computer business, and it was struggling. By the early 90s in the mainframe business, and by the mid-90s to 2000, really taking a bite out of the supercomputer industry. So even the supercomputer industry converted from customized special architectures into arrays of these general purpose microprocessors. They were just far too efficient in terms of cost and performance to be ignored. Now we're all of a sudden in a new era. We're in a new era, not because general purpose processors are going to completely go away. They're going to remain, they'll be important, but they'll be less centric to the drive to the edge, to the very fastest, most important applications, where the domain-specific processors will begin to play a key role. So rather than perhaps so much horizontal, we'll see, again, more vertical integration between the people who have the models for deep learning and machine learning systems, the people who build the OS and compilers that enable those to run efficiently, train efficiently, as well as be deployed in the field. Inference is a critical part of this. It means when we deploy these in the field, we'll probably have lots of very specialized processors that do one particular problem. The processor that sits in a camera, for example, that's a security camera, is going to have a very limited use, but a key is going to be optimized for power and efficiency in that key use, and cost, of course. So we see a different kind of integration, and Microsoft, Google, and Apple are all looking at this. The Apple M1 is a perfect example. If you look at the Apple M1, it's a processor designed by Apple with a deep understanding of the applications that are likely to run on that processor. So they have a special purpose graphics processor. They have a special purpose machine learning a domain accelerator on there. And then they have multiple cores, but even the cores are not completely homogeneous. Some are slow, low power cores, and some are high speed, high performance, higher power cores. So we see a completely different design approach with lots more co-design and vertical integration. We're optimizing in a different way than we have in the past. And I think this is going to slowly but surely change the entire computer industry. Not that general purpose processors will go away, and not that companies that make software that runs on multiple machines will completely go away, but we'll have a whole new driver. And that driver is created by the dramatic breakthroughs that we've seen in deep learning and machine learning. And I think this is going to make for a really interesting next 20 years. Thank you for your kind attention, and I'd like to wish the 2021 T-Edge conference a great success. Thank you.